Next, we're going to look at cell potentials under non-standard state conditions. Standard state conditions are defined as having solutions of 1 molar in concentration and any gases at 1 atmospheric pressure and a temperature of 25 degrees Celsius. Okay, all of our temperatures are going to be at 25 degrees Celsius unless we specify otherwise. Okay, so back in our thermodynamics chapter, we said that delta G non-standard is equal to delta G standard plus RT log Q. And using a couple of equations we came across earlier, under both non-standard and standard conditions, delta G equals minus NFE. N is the number of moles of electrons, F is Faraday's constant, E is the cell potential in volts. Right, so if we set these two quantities equal to each other and doing some substituting, we get E non-standard equals E standard minus RT over NF times log Q. Okay, here the 2.303 is a conversion factor for going from natural logs to base 10 logs. Okay, and the reason that we commonly use base 10 logs in electrochemistry is because of pH meters, and the pH scale is built on the base 10 logs. Okay, R is the gas constant in joules, T is the standard temperature, F is Faraday's constant. And so if we combine R, T, and N, okay, assuming T is a constant, okay, and taking that times 2.303, that's where we come up with this number. We're just combining all of this. And this is called the Nernst equation. And the units will be in volts. So here's an example of calculating cell potentials under non-standard state conditions. Here we have copper being oxidized to copper 2 and iron 3 being reduced to iron 2. Okay, so what is the cell potential at 25 degrees under the following conditions? Okay, so let's first calculate Q using these conditions that are given. Okay, and then we'll calculate the standard cell potential, which is 0.43 from values in the chart. And Q is products over reactants. Okay, we need to square the iron 2 and the iron 3. Okay, so we substitute those values in, calculate Q, substitute in for the Nernst equation, and then we get 0.25 volts. Okay, and this differs from our standard cell potential of 0.43. Electrochemistry can be used to determine pH. This is a pH electrode. It consists of a silver wire coated with silver chloride and contains a reference solution of dilute HCl and a thin glass membrane separating the reference solution from the test solution. Okay, so when this electrode is immersed in the test solution, its electrical potential depends linearly on the difference in the pH of the solutions on the two sides of the membrane. Okay, so under standard conditions, okay, if we take these two quantities and set them equal to each other, since they're both equal to delta G standard, we get our standard potential is RT over NF times log K. And again, combining these terms, we get 0.0592 volts over N. Okay, what this shows is that for a small change in cell potential, there is a huge change in the equilibrium constant. Okay, and it's not unusual for these equilibrium constants in these electrochemical reactions to have very large numbers. Okay, down here we have negative voltages, which mean non-spontaneous processes, and the equilibrium constants are very small. All right, so equilibrium constants can be calculated from concentration data. They can be calculated from thermochemical data, as shown here, and they can be calculated from electrochemical data. Okay, so an application of galvanic cells is the use in batteries. Right here we have the half reactions that are involved in the lead acid storage battery, which is what is commonly used in automobiles. The anode is lead. The cathode is lead 4 oxide or lead dioxide. Lead 0 or lead metal is getting oxidized to lead 2, which, because of the sulfate in solution, precipitates out as lead sulfate. Lead 4 oxide is reduced to lead 2. This is what's called a disproportionation, where the same element is oxidized and reduced. Okay, so here's the overall reaction. And this is the spontaneous reaction that occurs. Okay, so in a car, this would be what would happen if, for example, you discharged the battery. You left the lights on without turning on the engine. Okay, and then the battery would eventually run down. Okay, so what would happen is this white precipitate of lead sulfate would coat the electrodes, and then you would produce water. One of the ways that they test car batteries is to use this pipette that contains floating balls, and if the battery is good, you still have a lot of sulfuric acid, which is considerably denser than water, and so all the balls would float. But if the battery is run down, then you'll have a lot of water, and some of the balls would sink. Okay, this is a diagram of the lead acid storage battery. Each electrode consists of several grids with a large surface area, so the battery can deliver the high currents required to start an automobile engine. The sulfuric acid solution is the electrolyte, Then we've got a lead grid packed with spongy lead, which is the anode, and then we have another lead grid, which is packed with lead dioxide. Okay, a lead acid storage battery is an example of a rechargeable battery. And in modern cars, they use an alternator. In the older vehicles, a generator was used. The difference is that an alternator uses alternating current. Okay, so an alternator uses mechanical energy to convert to electrical energy, and then that electrical energy drives the non-spontaneous reaction of recharging the battery. Okay, so now we have an electrolytic cell when the battery is being recharged. Okay, so why isn't a car battery infinitely rechargeable? Okay, usually I have to replace my car battery every 3 to 5 years or so. There's several reasons. One is the casing material can fail and the electrolyte can leak. Another reason is that through repeated charges and recharges, you dissolve lead into solution, and then you reprecipitate the lead, and this goes on multiple times, and over time the lead that is deposited at the anode can become soft and it can break off. Okay, another problem that could happen over time is that when the lead redeposits on the anode, it forms these long fingers called dendrites. And in some cases, the fingers or dendrites can become so long that they end up touching the nearest plate, and this causes a short circuit, and then the battery fails. Okay, here's the reactions that take place in a dry cell battery. I don't necessarily expect you to remember this particular reaction. But this is about 1.5 volts. Okay, going back to the lead acid storage battery, if we were to calculate the overall cell potential from the chart, we would come out with 2 volts, approximately 2 volts. The majority of car batteries are 12 volts, and that's because they consist of 6 cells which are connected in series. Okay, and then this is simply a diagram of the dry cell battery. Here's an alkaline battery. This uses zinc and manganese 4 oxide. Okay, these are a couple of types of rechargeable batteries. In this case, the household batteries are placed in a charger, and then an electric current is supplied from a wall outlet. Nickel cadmium or NiCad batteries are not used so much anymore. They had some disadvantages. You could only recharge them about 50 to 60 times, and then they would just fail after that. The other disadvantage is that cadmium is an extremely toxic metal. These have been largely replaced with nickel metal hydride batteries. These are the 2 half reactions that occur at the anode and the cathode. Lithium and lithium-ion batteries are used in a variety of consumer electronics, such as cell phones, laptop computers, and even some smoke detectors use these batteries. The lithium battery was originally developed to power pacemakers. Heart pacemakers, when they were first invented, would fail after 2 to 3 years. And the failure mechanism was always the battery. And when this lithium battery was developed and used in heart pacemakers, the lifetime was increased to 10 years or more. Today, heart pacemakers actually use a radioactive isotope, plutonium-238. But lithium and lithium-ion batteries are still widely used in a variety of places. Also, they're used in electric cars. Okay, I'll briefly talk about the hydrogen-oxygen fuel cell. The net reaction here is the conversion of hydrogen and oxygen to water. Hydrogen is oxidized to water at the anode, and then oxygen is reduced to hydroxide at the cathode. And this uses porous carbon electrodes containing metal catalysts. The fuel cell is used on the International Space Station, for example. There's some experimental uses of fuel cells in cars, but so far it's not very cost effective. In the next lesson, we're going to talk about corrosion.